Hello, welcome to the Better by Book channel. In this episode, we'll be exploring a milestone in global scientific literature, A Brief History of Time by Stephen Hawking. In about 20 minutes, I'll walk you through the essence of this book. What contributions did Hawking make to our understanding of the universe? A Brief History of Time is probably the most famous and best-selling popular science book in the world. After its publication in 1988, it stayed on bestseller lists for 237 consecutive weeks, or about 4.5 years, setting an unprecedented record. The book has been translated into more than 40 languages, and it is said that worldwide, 1 out of every 750 people owns a copy of A Brief History of Time. So one of Hawking's postdoctoral students once jokingly remarked that Hawking's science writing sold even better than Madonna's books about sex. The author of A Brief History of Time, Stephen Hawking, is also one of the most famous and legendary scientists in the world today. This is because although Hawking suffered from amyotrophic lateral sclerosis and was confined to a wheelchair, he still relied on his extraordinary intellect to make tremendous contributions to modern physics, especially in the study of the Big Bang and black holes. During his lifetime, Hawking was the Lucasian Professor of Mathematics at the University of Cambridge. This position was once held by scientific giants such as Isaac Newton and Paul Dirac, so Hawking's academic achievements are truly remarkable. The content covered in A Brief History of Time is extremely broad. From relativity to quantum mechanics, from cosmic expansion to elementary particles, from black holes to wormholes, Hawking introduces all of these topics. So after reading this book, you may gain a deeper understanding of science fiction films like Interstellar, which involve many physical concepts. But to be honest, A Brief History of Time is not very friendly to ordinary readers. For many physics concepts, Hawking provides only brief explanations, and some are mentioned only in passing. Readers without a solid background may not understand what Hawking is talking about at all. Some surveys have even found that most people forget almost everything in the book except for the jokes at the beginning. It's almost as if they hadn't read it at all. As a result, Hawking later published A Brief History of Time, a reader's companion hoping to make his theories more accessible. Later still, with the help of the Hubble Space Telescope and computer-based 3D and 4D imaging technology, an illustrated edition was released, adding more than 200 color illustrations to help readers better appreciate the wonders of cosmology. As a classic work of popular science, the true uniqueness of A Brief History of Time lies in the fact that it introduces Hawking's own major theoretical contributions. Hawking's most important academic contributions are his studies of singularities and black holes. Roughly in chronological order, these include: First, Hawking and the British mathematician Roger Penrose jointly proved the famous singularity theorems, which are related to general relativity and cosmic expansion. Second, Hawking proved that black holes can emit radiation, now known as Hawking radiation. Third, Hawking proposed the no-boundary universe model, arguing that the universe has no boundaries, no beginning, and no end, posing a direct challenge to the concept of God. Hawking introduces all of these theories in A Brief History of Time. So next, we'll use these theories as our entry point to explore the essence of the book. What contributions did Hawking make to our understanding of the universe? First, we'll look at what the singularity theorem proposed by Hawking and Penrose actually is. Second, we'll examine what is special about Hawking's no-boundary universe model. Third, we'll see why Hawking said that black holes are not completely black. First question, what is the singularity theorem? Before the 20th century, people generally assumed that the universe was static. Even though Newton's law of universal gravitation showed that objects attract one another, people still came up with various explanations to maintain the idea of a static universe. Even Einstein stumbled on this issue. In 1915, Einstein published the theory of general relativity, proposing that spacetime can be curved. According to his equations, the universe is not static. But Einstein believed there must be something wrong, so he forcibly added a cosmological constant to his equations, making the universe appear static once again. In the 1920s, however, scientists discovered while observing other stars that many of them exhibited a phenomenon called redshift, meaning they were moving away from Earth. At first, people thought stellar motion was random, some stars moving away, others moving closer. But in 1929, American astronomer Edwin Hubble, the namesake of the Hubble Space Telescope, discovered that most stars are moving away from Earth, and the farther away a star is, the faster it is receding. What does this tell us? Imagine drawing several dots on the surface of a balloon, then blowing it up. As the balloon expands, the dots move farther apart, and the farther apart two dots are, the faster they separate. The balloon represents our universe, and the dots represent Earth and other stars. Since most stars are moving away from us, this indicates that the universe is continuously expanding. After learning of this observation, Einstein realized that the cosmological constant he had added was completely unnecessary. The universe is not static, it really is expanding. Einstein later said that the cosmological constant was the biggest mistake of his life. After discovering cosmic expansion, scientists developed a new model based on general relativity to describe the expanding universe. The Friedmann model, first proposed by Alexander Friedmann. Calculations showed that in this model, if we trace time backward, the universe contracts. If we go back about 15 billion years, the distance between all galaxies becomes zero, as if the entire universe were compressed into a single point. This point is called a singularity, and it represents the beginning of spacetime. A singularity has very peculiar properties. It is impossible to imagine intuitively, but mathematically we find that its volume is infinitely small, while its curvature, density, and gravitational force are infinitely large. Mathematics cannot truly handle infinities, which means that although the Friedmann model is derived from general relativity itself breaks down at the singularity. Hawking therefore argued that the appearance of a singularity proves that general relativity is an incomplete theory. It fails at the very beginning of the universe. In other words, general relativity predicts its own collapse. Once we understand what a singularity is, we can examine Hawking's contribution and how he viewed singularities. When the singularity concept was first proposed, not all scientists accepted it. According to Hawking, even Einstein himself was skeptical. Einstein believed that if we trace time backward, galaxies would not collide into a single point, but would instead narrowly miss one another. Two Soviet scientists also argued that singularities might be rare special cases in the Friedmann model, and might not exist in the real universe. However, after reading the work of mathematician Roger Penrose, Hawking became convinced that singularity theory was correct. After years of research, Hawking and Penrose used rigorous mathematics to prove that if general relativity is correct, and if the universe contains as much matter as we observe, then the universe must have originated from a singularity. This result is known as the Penrose-Hawking singularity theorem. Some people initially resisted this conclusion because they disliked the idea that the universe had a beginning. Others felt it violated scientific determinism or undermined the elegance of general relativity. But Hawking and Penrose were not speculating. They proved their results mathematically. And mathematics does not lie. From then on, whether they liked it or not, almost all scientists accepted that the universe did indeed originate from a singularity. So that answers the first question: what is the singularity theorem? Before the 20th century, people believed the universe was static. After discovering cosmic expansion, scientists realized that around 15 billion years ago, all galaxies converged to a point of infinite density, curvature, and gravity. Hawking and Penrose proved that if general relativity is correct, the universe must have begun at such a singularity, the beginning of the universe. Second question, the no-boundary universe model. Although the singularity theorem is one of Hawking's greatest contributions, he later changed his thinking and proposed the no-boundary universe model, arguing that the universe does not need to originate from a singularity. According to the Big Bang theory, the mainstream model of cosmic origins, the universe began at a singularity known as the Big Bang singularity. In the Big Bang model, The universe had zero volume and infinite temperature at the beginning. As it expanded, its temperature dropped. After 1 second, it cooled to about 10 billion degrees. After 100 seconds, protons and neutrons formed atomic nuclei. After 1 million years, atoms formed. Later, galaxies and stars emerged. Even today, scientists can detect leftover energy from the Big Bang, called cosmic microwave background radiation. Although the Big Bang theory fits observational evidence, it raises an awkward question. The Big Bang represents the beginning of time and space, where physical laws break down. So where did those laws come from? Who set them? Was it God? Hawking addressed this question with the no-boundary universe model, arguing that when quantum mechanics is combined with relativity, the universe can be finite but without boundaries, much like the surface of the Earth. In such a universe, there is no singular beginning, and therefore no need for a creator. Hawking emphasized that this model is still hypothetical and not the mainstream view, but it is a scientifically testable attempt to unify quantum mechanics and relativity. Third question, why black holes are not completely black. Hawking's third major contribution concerns black holes. Although black holes have gravity so strong that even light cannot escape, Hawking showed that they can emit radiation. Using quantum theory and the uncertainty principle, Hawking demonstrated that particle pairs constantly appear near the edge of a black hole. Some particles fall in, while others escape, making it appear as though the black hole is emitting radiation. This phenomenon is known as Hawking radiation. Final summary. To summarize Hawking's contributions, as presented in A Brief History of Time. First, the singularity theorem, proving that the universe must have begun at a singularity if general relativity is correct. Second, the no-boundary universe model, suggesting a universe that is finite but without boundaries, eliminating the need for a beginning or a creator. Third, Hawking radiation, showing that black holes are not completely black, but emit radiation due to quantum effects. These ideas together form the core of A Brief History of Time, and represent Stephen Hawking's profound contributions to our understanding of the universe.